Hello everyone. In this video, I'm going to show you a compact 3-in-1 handheld instrument I purchased from Banggood. The device arrives in this box. Let's take a look at what's included. A USB-C charging cable, an English and Chinese user manual, 2 test leads, a 100 MHz oscilloscope probe, and a BNC to alligator clip cable for the signal generator. I'll set the accessories aside for now, and here's the instrument itself. Why did I buy this device when I already own many similar tools? You can see some of them in this photo. A few years ago, there was a Hungarian car commercial. Unfortunately, it was made only in Hungarian, and due to copyright, I can't show you the video. Just a single still image. But I made my own remake of it. Here it is.
Do you like it?
Yes.
Do you have a big family?
No.
Are you looking for a car for weekend trips or vacations?
No.
Do you need this car at all?
No.
Then why?
I just want it.
And yes, I felt something similar when I first saw this instrument on Banggood's website. I didn't really need it, but I wanted it. What caught my attention was that it looks like a multimeter, but it's also an oscilloscope and a signal generator in one. Other devices with similar functions don't have this nice rotary selector switch. So let's see how it works. On the side, the blue button is the power switch. Under this rubber cover is the USB-C charging port. On the front end, the left BNC connector is the generator output, and the right BNC is the oscilloscope input. On the back, it has a kickstand so you can use it in an upright position. The multimeter input jacks are at the bottom front. When you power it on, it displays the manufacturer's name, FNIRSi. And on this screen, you can select which of the 4 options you want to use. The horizontal arrow keys let you scroll through the 4 choices: settings, signal generator, oscilloscope, multimeter. If you use one function more often, you can set it as the default startup mode. There are also day and night display themes. You can set how long it waits before powering off automatically. Via USB, you can share screenshots and measurement data. Here's the software version. You can restore the factory settings. You can choose between Chinese and English languages. You can also adjust both the volume and the brightness. You can switch functions with the mode button as well. This is the signal generator. This is the multimeter. And this is the single trace oscilloscope. Let's start exploring the multimeter. Now the 2 instruments are connected in parallel for DC voltage measurement. With this small reference source, which has its exact values written on the bottom, we'll take measurements. Turning it on. First, we should get 2.5 volts. We can see that the instrument measures accurately. This is now the 5-volt output, and it measures that very nicely as well. Next is 7.5 volts. Again, the reading is spot on. And finally, the 10-volt setting, also showing the correct value. I do have a much more precise instrument, but I can't place it under the camera like this because its display is on the side. Now let's measure AC voltage. Here you can see an extension cord. Switching to AC mode, it measures that correctly as well. Now let's measure AC current. For this, we need to connect the instruments in series. We'll measure the current of this light bulb. Here we can see that both instruments show the same value, so it's also excellent for AC current. Let's measure a higher DC voltage: 60 volts, 50 volts, 40 volts, 30 volts, 20 volts, 10 volts. We always need to wait until the output capacitor in the power supply discharges. Let's measure resistance. This is a precision resistor standard. Its value is 4.9996 kilo ohms. Let's check it. It measures perfectly. Let's also check it with the other fluke meter. It reads exactly the same. Now let's measure a reference capacitor. Its value is 60.097 nanofarads. Let's check it. It measures 60.47 nanofarads, including the parasitic capacitance of the test leads. Let's measure the same with the fluke. .3 nanofarads. Additionally, it measures capacitance accurately. Let's measure some very precise resistors. Here is a 500 kilo ohm resistor with 0.005% tolerance. Let's check it. It measures perfectly. Here is another one with the same tolerance, 2.5 kilo ohms. It measures beautifully. A 4 kilo ohm resistor. Perfect reading. Here is a 30 kilo ohm resistor. It measures exactly 30 kilo ohms. Here is a 1 megohm resistor. It reads exactly 1 megohm, so it's also excellent for resistance measurement. Let's measure DC current. At 10 amps DC, there is already a slight difference. 1 ampere, 2 amps. 3 amps, 4 amps, 5 amps, 6 amps, 7 amps, 8 amps, 9 amps, 10 amps. Let's measure ACRMS value. 50 Hertz, 5 volts, RMS value. It measures slightly lower. Let's check the same at 100 Hertz. At that frequency, they read almost the same. 200 Hertz, 400 Hertz, 1 kilohertz, 5 kilohertz. Here it no longer measures accurately. 4 kilohertz is also not accurate. It can measure RMS values up to 2 kilohertz. This is now 2 kilohertz. Let's measure frequency with it now. 1 kilohertz, 100 hertz, 10 hertz, 1 hertz, 10 kilohertz, 100 kilohertz, 1 megahertz. The fluke doesn't measure this anymore. 10 megahertz, but this one still measures it. 20 megahertz, it measures this as well. 21 megahertz, 22 megahertz. It can still measure 23 megahertz. At 24 megahertz, it starts to make errors. So that was the frequency measurement. In multimeter mode, there is also an option to log the measured values. Now I'm increasing the voltage, and the instrument stores these measured data nicely. Now let's take a look at the oscilloscope mode. Right now, I have applied a simple 1 kilohertz sine wave, which fills the screen, so it will be easier to compare at higher frequencies. Here, there is a V and an H letter, which means that with V, the up and down arrows, you can adjust the vertical sensitivity, and H, the left and right arrows, adjust the time base. If we press the Enter button again, it changes into 2 arrows. The black arrow means we can move the waveform horizontally, and the green arrow means we can move it up or down. If we press Enter once more, The first green arrow remains, so we can still move horizontally with the horizontal cursors, and with the vertical one, we can adjust the trigger level. If we press again, we return to the V and H letters. Now let's see, we've applied this 1 kilohertz signal. Now let's apply 1 megahertz. This requires a smaller time division. So, same size. Now let's apply 2 megahertz. 3, it already drops a bit. 4, 5, 6. Here we can still zoom in once more horizontally. 7, 8, 9, 10, 11, 12, 13, 14, 15. But here it's no longer usable. It's no longer sampling correctly here. Here you can see the types of measurements it can perform in oscilloscope mode. Let's take a look at the signal generator and see how it works. We could test it with itself, but that would be a bit more complicated because it only has a shared screen. So now we will examine the signals using an external oscilloscope. Here you can see the generator menu. With the Run button, we can start generating the signal. Here we see the beautiful sawtooth wave. Let's measure its frequency. This is 1 kilohertz. We can set the frequency with multi-digit precision. We can adjust the duty cycle. If we go into any of the fields, we can change the numbers using the Enter key. And pressing Enter again will exit the field. We can set the amplitude. Enter. Let's set the signal to only 2 volts. We can adjust that too. The maximum is 3 volts. Let's see what other waveforms we can create. If we select the waveform using the Auto button, we can switch between them. Square wave, sine wave. It starts with sine because that's the most basic signal. We can see this is a digital sine. Square wave, sawtooth wave, half wave, full wave, step wave, reverse step wave, index up, index decrease, and we can also output DC voltage, multi-audio, sync pulse, Lorentz waves. These are the signals we can generate. Let's see, for example, what the maximum frequency is for the sine wave. So we can generate sine waves up to 50 kilohertz, square wave, sawtooth, and all other signals too. Here the signal is no longer so stepped. In the next part, I connected the generator output to the oscilloscope input with this short cable. And now I will show some settings on the instrument that I haven't demonstrated yet. Right now, we see no signal because there's only a line in the middle. That's because in the top left corner, that red sine wave icon indicates the generator is off. Let's go to the generator menu. And if we press the Run button here, it turns green, and if we now go back to the oscilloscope, we can see that the signal has appeared. This signal is above 0 because the instrument has no negative supply voltage. Therefore, it generates every signal between 0 and the maximum. If we want to see this more clearly, we have 2 options. Either move it down with the vertical positioning control I showed earlier, or switch from DC coupling to AC coupling. I haven't shown this yet, so let me demonstrate it now. Press and hold the Mode button, and a new menu will appear. This is the coupling setting that is currently selected. We can change it with the Enter button. And if I press and hold the Mode button again, we can see it has been applied. Now the signal is nicely centered. The trigger event is here in the middle, under the green arrow. So the signal starts going upward from here. Now, for example, if we go back, here we could set the probe attenuation, but this cable is 1 times, so we'll leave it as it is. Below that, we could set the trigger mode, whether it should be normal, auto, or single-shot sampling. And below that, we can set which edge it should trigger on. Now, if I change this with Enter and go back, we can see the sine wave is now going downward in the middle. Let's see what else can be set. If we press and hold the Mode button and move horizontally, here we can set the measurements. By default, if we select all off, it will turn off all measurements. And if we go down with the down arrow, we can turn on, for example, frequency measurement, or let's say the period measurement. Here we just go step by step, and perhaps also the VPP measurement. Now we go back again, and we can see it displayed these: 1 kilohertz, 1 millisecond, and amplitude 3 volts. If we select all on, it will turn on all measurements, and now we can see all the parameters. If we go back, right arrow, go down 1, and press Enter now, it will turn off all of them. Here it is. Now if we go further horizontally in this menu, we can set how long to display the samples on the screen. This is the persist mode. It is off now, but it can collect traces for half a second, 1 second, or indefinitely. If we go one more step, here we can see the images we have saved earlier, and we can view them with the Enter button. Here's the first image. It looks like this because I saved it in dark mode. Here's the second image, and here's the third image I saved. And we can exit from here by pressing and holding the Mode button. This is the device's night mode, also called dark mode. Here's how the multimeter looks. Here's how the oscilloscope looks. And here's how the generator looks. So here, for example, is a signal. If we briefly press the Run Save button, it stops. If we press and hold it, it saves a BMP file. Now we switch to a square wave and save that too. Switch to a triangle wave and save that as well. And then, if we press and hold the Mode button, here under Image, we can see the saved pictures. I'll now read them out with the computer, and then I'll show them there as well. To do this, first select the lowest menu item in the Settings menu, USB sharing. Then, by pressing Enter twice, the device will act as a USB drive, and we can copy the saved files from it. In this picture, you can see that when the instrument is connected to the computer, it appears as a nameless drive with an MS-DOS FAT12 file system of 5.2 megabytes, with 2 folders inside. The one called Logo is empty, while the saved images are in the folder named Screenshot File. Since the device does not have a real-time clock, the folder dates are always January 1st, 1970 at 1 a.m., while the image files are dated December 31st, 2019 at 2300 hours. In this picture, the saved images are shown in icon view, and when the icons are enlarged, they are clearly visible. The saved images have a resolution of 320 by 240 pixels, so in this HD video, they look very pixelated. Let's look at them one by one. This is the saved sine wave image. This one shows the saved square wave, and here is the saved triangle wave. Well, that was a quick introduction to this small instrument. I think it's quite usable, and I really like its appearance. If anyone is interested in buying it, the link to the instrument on the Banggood online store is in the video description. Thank you for watching this video. It's hard to believe, but I spent several days working on it. That's why I especially appreciate every single like. If you enjoy this kind of technical content and haven't subscribed to my channel yet, now's a great time to do it. See you in the next or even an earlier video. Goodbye.